terrible. It's basically stuff that you guys have already heard about before. So let's go ahead and look at this journal together. It would help if it was connected. That'd be lovely. All right, so we're looking at our journal. So these are all the key features that we're going to be looking at today with rational functions. So we're going to start with the key features that are probably the most unfamiliar to you guys, which is the vertical asymptotes and the holes, as well as the horizontal asymptotes. So let's look at vertical asymptotes first. So we kind of touched briefly on this when we talked about exponential and logarithmic graphs. So does anyone remember what an asymptote actually does? So I'll give you a hint. When we did exponential and logarithmic graphs, each one had a type of asymptote, whether it was horizontal or vertical. And it did something to the graph. What do you think it did? So, for example, and you don't need to graph this, but if I had y equals 2 to the x power, this is an exponential graph. It has a horizontal asymptote at y equals 0. So it's the x-axis. What's happening to that graph? What's happening as it gets to 0 when x is 0? So what happens as it's getting closer to the x-axis? It gets closest to it, but does it ever cross? No. That's what an asymptote is. An asymptote is a line that the graph never crosses, whether it's a vertical or horizontal. So a vertical asymptote is a vertical line that the function will never cross. Now, this occurs when we simplify our factors in the denominator. All right, so that's when we, way back with 4.2, that's when we would factor it, cross out the stuff that has in common. The vertical asymptote is whatever that last factor is in the denominator, or factors. So it's written as x is equal to the root of the remaining factors. So in other words, whatever factor you would have left over, that's what you would set equal to 0, solve for x. So you guys may not even get what I'm talking about, but let's just go ahead and factor this real quick. So let's look at this example. We're going to simplify this example. So first off, we need to factor the numerator and denominator. So let's factor the numerator first. What are two numbers that multiply to -6 but add to 1? +3 and -2. So this would be x plus 3 times x minus 2 all over. And you could do big X too if you need to, but we're trying to do this quickly. So, what are two factors of -3 that add to 2? +3 never -1. So this would be x plus 3, x minus 1. So if I'm simplifying, what factors can I cross out? X plus 3. So these go away. I'm left with x minus 2 over x minus 1. Your vertical asymptote comes from whatever's left over in my denominator. This right here gives me my vertical asymptote. And the way I find it is I set it equal to 0 and solve for x. So I would do x minus 1 equal to 0. So my vertical asymptote is at x equals 1. So on my graph, if I were to graph this, I would have I think that's a TB. So we would have a vertical asymptote at x equals 1. So on your graph, I would draw a vertical line at the x value of 1, so right here. And we typically draw asymptotes with dashed lines. So this is my vertical asymptote. And again, it's at x equals 1. Now, on the other end, there's a hole. So the hole also comes from the act of simplifying your rational. And the way that works is that the hole occurs. So the hole occurs when factors cancel while simplifying. So in other words, we use whatever factor we canceled out to get our hole. So the x value of the hole is equal to the root of the cancel factor. The y value comes from by substituting x into its simplified form. So, biggest thing to note with a hole is a point. So a hole is a point. So point xy. Your vertical asymptote is a line. So that's the difference between the two. The hole is a point. The vertical asymptote is a line. The x value of the point comes from the factor that we canceled out. So let's look back at this example. All right. What factor did I cancel out from this example? X plus 3. Because that's the factor that we use to cancel out, that's what I'm going to set equal to 0 to get my hole. So my hole, or the x value anyway, the hole, specifically the x value, comes from that canceled out factor. So if I set x plus 3 equals 0, the first part of my hole is that x is equal to negative 3. That's just the x value of the hole. But since the hole is a point, I need to find the y value. The way I find that is I take the negative 3 and plug it back into both x's in the simplified form to get the y value. So I would have negative 3 minus 2 over negative 3 minus 1. And that would give me the y value, so equal to y. So what's negative 3 minus 2? That's negative 5. What's negative 3 minus 1? Negative 4. So my y value, y is equal to 5/4. So when I put it all together, I'm taking the x and the y value, putting it together in a point. My hole is at the point negative 3 and 5/4. Now, when we graph it, all right, when we graph it, we're going to draw an open circle. So it will literally look like a hole that you would fall into. That's a good way I remember it. The hole is the open circle that you can fall into. Why do you think I'm going to use an open circle? It won't touch that point. It'll never be defined at that point. Just like with the vertical asymptote, it would never be defined at x equals 1. Well, it would never be defined at this hole either. And the reason that is because at some point, because of our original, all right, remember what I said yesterday. What makes an extraneous solution with a rational? What can we not have in a rational function? That's a radical function, rational. We cannot have 0 in the where, in the denominator. So the reason why is if we look at our original simplified version, if we set both of these equal to 0, we could not have an x value at negative 3 or an x value at 1. Because if we do, it would make the denominator what? So if I plugged in negative 3 for x, what's negative 3 times 3? Or negative 3 plus 3? 0. What's 0 times anything? 0. If I plugged in 1 in for x, what's 1 minus 1? 0. What's 0 times anything? 0. So those are the two x values that would make this function undefined. It cannot equal those x values. That's what these asymptotes are finding, as well as the whole. It's finding at this line or at this point, we cannot have this x value. It's undefined there. So that's another way you can look at it. Both of these, we're looking for, so for both of these, we're looking for x value that is undefined, whether that be in line form or in point form. And that's where the difference between whole and vertical asymptote come in. So graphing my whole, I'm going to go over to -3 and then 5/4, which is a little bit over 1, so about right here. And I'm just going to draw an open circle. That's my whole. So at this point right here, there's nothing, just empty space. All right? It won't be part of my graph. So, any questions on how to find vertical asymptotes or wholes? So again, the difference between the two is both of them, you got to simplify. All right? Both of them you have to simplify first. But the difference is that this one you get from the denominator of your new simplified fraction. This one comes from the factor that you crossed out, or factors that you crossed out. There can be multiple wholes, there can be multiple vertical asymptotes. All right, so be careful about that. Any questions on that part? All right. Now, horizontal asymptotes. So this is a horizontal line that the graph cannot cross. So again, a horizontal asymptote is a horizontal line where the graph levels out at x and the graphs don't necessarily cross. Sometimes they do, sometimes they don't. So when it comes to rational functions, sometimes they cross the horizontal asymptote, but it's very, very rare that they do. All right. Now, the horizontal asymptote comes from the original function. All right. So horizontal asymptote comes from the original function. It is written as a line. All right. And we always write as y equals some number. And it comes from the original function. Now, there are three circumstances that will give us our horizontal asymptote. And if they follow these rules. So the first case you can have, it's all based off of the degree of the numerator and denominator. Who remembers what degree means? If we're looking at the degree of a function, what are we looking at? The highest exponent. So the highest exponent in the numerator versus the highest exponent in the denominator. So it comes from the original function, the unfactored version. Now, if your numerator has a lower degree than your denominator. So another way to write it is if your numerator degree is less than your denominator. Your horizontal asymptote is automatically y equals 0. If your numerator and your denominator have the exact same degree, meaning that their highest exponent is exactly the same, so it equals. What you do is you take the leading coefficient or the number in front of the highest exponent of the numerator and divide it by the leading coefficient of the denominator, and that gives you your horizontal asymptote. And I'll do some examples of this. And then lastly, if your numerator is higher than your denominator, so the degree of your numerator is higher than your denominator, there is automatically no horizontal asymptote. It doesn't exist. Now, we don't learn this in this class, but there could be a slant asymptote, which is a diagonal line that they can't cross, but we don't learn about that in this class. All right. So if I look at my original function up top, all right, it doesn't ask us to find it, but we're still going to find it. What do you think my horizontal asymptote is? So first off, let's look at the degrees of the function. So I'm going to find my horizontal asymptote. What is the highest exponent of my numerator in the original function? So this one right here. What is the highest exponent in my numerator? 2. All right. So my highest exponent in the numerator is 2. What is in the denominator? 2. So the degrees are what? If the degree is 2 here and 2 here, that means they are what? The same. So in this case, my numerator equals my denominator. So that means that I take my leading coefficients, so the numbers in front of these exponents, which in this case, they're both 1. I take these two numbers, put them over each other. That's my horizontal asymptote. So that means that y is equal to 1 over 1, which means my horizontal asymptote is at y equals what? Y equals 1. That's my horizontal asymptote. So on the graph, my horizontal asymptote, I'll go to when y is 1 and draw a horizontal line. So it looks something like that. That's my horizontal asymptote, or HA, at y equals 1. Now, if I looked at some other examples, so let's look at right here, these two examples. All right, look at the leftmost example. So these are the original functions. We're not simplifying them. First off, what's the degree of my numerator? 2, because that's my highest exponent. So since this exponent is 2, the degree is 2. What's the degree of the denominator? 2. That's the highest exponent. So you're just looking at the exponent to determine the degree. So that means my degrees are what? Equal. So in this case, the numerator equals the denominator in terms of degrees. So because of that, I'm going to take my two leading coefficients, so the 2 and the 4, because that's what they're attached to, the variable with the highest exponent. And I'm going to put them over each other, and that's my horizontal asymptote. So this would be 2 over 4, which simplifies down to what? 1/2. So my y is equal to 1/2. That's where my horizontal asymptote is, at y equals 1/2. What about my other one? So what's my degree of the numerator? 2. That's the highest exponent in the numerator. What is in the denominator? 1, because remember, the unspoken exponent here is 1. So, which is bigger, the numerator or the denominator? The numerator. So, if the numerator is greater than the denominator, what's my answer for my asymptote? So, what does the conditions up here say? If my numerator is greater than my denominator, there's no asymptote. Good. So, there's no horizontal asymptote. So, guys, that's why you need to know these 3 conditions. So, if the The hardest one is the second one. The other two are really easy. All right. If the numerator is less than the denominator, it's y equals 0. That's your answer. If the numerator is greater than the denominator in terms of the highest exponent, you have no horizontal asymptote. That's your answer. The hardest one is the second condition. If they have the same degree, you just take the two leading coefficients, which is usually the first two numbers, by the way, and put them over each other, simplify it down, that's your answer. Does that make sense? All right. Any questions on asymptotes of any type? So vertical, whole, or horizontal. All right. Now we're going to look at ones that you already know. So x and y intercepts. You should already know what an x-intercept is. It's when, it crosses the x-axis. Y-intercept is when it crosses the y-axis. All right. Now, your x-intercept comes from your simplified version of your function. Your y-intercept comes from your simplified as well. Both of these come from your simplified function if you were to do it by hand. If not, just look at the graph in Desmos. But we're still going to solve it by hand just for right now. So, if I want the x-intercept occurs when the numerator is 0. So we just have to find the roots of the numerator. All right, so for example, up top with this original function, I'm looking at my simplified function, or this one right here, so the x minus 2, x minus 1. My x-intercept is going to come from this numerator right here. I'm going to set x minus 2 equal to 0 and solve. So down below, my x-intercept of my top function would be x minus 2 equal to 0, so x equals 2. So as a point, what would my x-intercept be? If x is equal to 2 for the x-intercept, what is it as a point? 2, 0. So that's my x-intercept for this graph. So my x-intercept here, 2, 0, that means it's right here. That's my x-intercept. Now, your y-intercept comes from when you put 0 in for x in your simplified function and solve for y. So in other words, you're finding when x is equal to 0 and you're going to substitute it into your simplified function. So my simplified function up top is y equals x minus 2 over x minus 1. I'm going to take this 0, plug it in for both x's, and evaluate that, and it'll give me my y-intercept. So y is equal to 0 minus 2 over 0 minus 1. So I would get negative 2 over negative 1, which is what? 2. So my y-intercept is at y equals 2. What's that as a point? 0, 2. So as a point, this would be at the point 0, 2. So up top, I will graph my y-intercept at 0, 2. Now, I have enough information at this point to get kind of the general shape of the graph. But to check, let's graph the original function in Desmos. So I'm going to take a minute and graph that original function in Desmos. So in Desmos, and you guys can do this along with me, do y equals x squared plus x minus 6. And you may have to throw parentheses around it to do the fraction bar. All divided by x squared plus 2x minus 3. And your graph should look something like that. Now, just for funsies, I'm going to show you where the vertical and horizontal asymptote is. So I said my vertical asymptote was where for this graph? X equals 1. So I'm going to graph x equals 1. It would help if I actually put the x. And then my y, and then my horizontal asymptote was where? Y. Come on, computer. Y equals what? Y equals 1. Is that what I wrote? Y equals 1? Okay. So, look at the graph now. The horizontal and vertical asymptotes are those two lines. Does it look like your graph crosses the line, those two lines at any point? No. Now, I want to look where my hole is. So Desmos doesn't graph your hole, but the way you figure it out is that if you ran your pencil along the graph, what x value did we have a hole at? When x equals what? -3. So I'm going to hit my pencil right on top of where it says -3. Do you see what happens when I'm hovering over -3? What happens? What does it say for the y value? It's undefined, and it actually shows that little tiny hole there. All right, it doesn't originally graph it, but if you hover your pencil over it, it will actually say it's undefined there. All right, so there actually is a hole or a point that's undefined. All right. Now, I'm going to draw the general shape, and the best way to do it is to just look at your horizontal and vertical asymptotes because they kind of dictate what the shape will look like because you don't want to cross them. So your shape of the graph would look something like this. Y. Just Y. Thank you. So that's what your graph would look like. And again, your horizontal and vertical asymptotes are really good distinguishers for that. That's why it's really good to find those things first. Now, from there, we can find things like our domain and range and end behavior. So your domain for your function is all real numbers except where the x values for your VAs and your holes. So remember, your domain is x values. So obviously, wherever your graph doesn't cross is where your domain is. It can be written in a couple of ways. So it can be written as x equals some number or cannot equal some number. These are your excluded values. Or we can write it in set builder notation. So for the example next to us, what x values were we not allowed to have? So for this graph, what x values were we not allowed to have at? So what were the x values of our vertical asymptotes and our holes? So there are two x's that our graph could absolutely not equal to. What are those two x's? Guys, what's your vertical asymptote and what x value is your hole at? Couldn't have an x at x equals 1. Can't have one at -3. It's literally the x values of your vertical asymptote and your hole. We already found them. So if I was to write this domain, I would write it in set builder notation. So what do I always start with? What's my lowest x value? -infinity. What's my first stopping point numerically? What's the first x value that I can't cross? -3. And we'll put a parenthesis there because we can't cross it. Then I'm going to draw my union symbol because it picks up again after -3 to where? Where does it stop again? At what x value? At 1. Put another union symbol, and it goes from 1 to where? Positive infinity. So this right here would be how I write my domain. All right. First, you figure out what x values you can't cross at, and then you just write it in numerical order. So you first have from -infinity to your lowest x value you can't cross, then the two x values you can't cross together, then your highest x value you can't cross to positive infinity. That's typically how you write your domain. Any questions on that one? All right. Let's do some other examples with this. So with these functions, it doesn't ask us to find the domain, but you know what? We're going to do it anyway. So we're going to find the domain of these functions. And for that, we're just going to use Desmos for this. So take a minute, graph that leftmost function in Desmos. So the 2x squared minus 3x over 4x squared minus x minus 3. So y equals 2x squared. Okay, so this one's a little bit of a weird one. This one looks like it has two vertical asymptotes. And the way I can tell is because it looks like it's not passing two different lines. So if I had to guesstimate my vertical asymptotes, this first one over here, where does it look like it will not cross? So if we get closer, it's about halfway between -1 and -2. So what do you guys think? The vertical asymptote would be where? Okay, you know what? Screw the domain for these. We're not going to do those. It's a little too difficult. All right. So next we have range. So we can check the graph, but usually it's all real numbers except the horizontal asymptote and the y value of our hole. So horizontal asymptote and the y value of your hole. So up here, it's the x value of your hole. Down here, it's your y value because range, we're looking for y values. And it's written as y is cannot equal some number. So for our current graph, what values can our y not equal? So it can't equal 1, and what's the other value? And it can't equal 5/4. So 5/4 is the y value of my hole. 1 is my horizontal asymptote. So to find it, so my range in this case would be, we start at -infinity to where? Where does it stop for the first time? What's my lower end of the excluded y values? 1. Then we go from 1 to 5/4. and then from 5/4 to infinity. So essentially, you're just putting it, not commas, you're going to put the union symbol. So essentially, you're putting everything in numerical order, but you're just noting where the stopping points are, where they can't cross. That's what we're noting. We're saying that there's graph between negative infinity and 1 y values. There's graph between these two y values, and there's graph here. That's what this means. So let's look at the range for this one. We don't even have to look at the graph for this because we already have the horizontal asymptote, right? Yes, no, maybe? Yes. So, all right, our range, where do you think it'll be? So first off, it can't include what? What value can our range not include? 1/2. So it cannot include 1/2. So that means I start where? Where do you always start with any? What's your lowest y value? Negative infinity. Where do I stop? 1/2. Then it goes from where? Where's it pick up again at? 1/2 to where? Infinity. That's how we would write that range. For the other one, there's no horizontal asymptotes. But since there's no horizontal asymptote, we gotta check the graph for range. Because clearly, if we look at the graph, there are some values where the y's don't cross. So, this isn't the graph we're looking at. I'm going to graph the second graph. So, we're going to graph y equals x squared minus 4 divided by, that's not what I wanted. Ugh. Divided by x plus 3. Our graph looks really funky. All right. So, what do you think my lowest y value is? Oh, actually. So you might have to zoom out a bit to see the full graph. So, if we start from bottom to top, all right, this is one of those cases where it has a slant asymptote instead of a horizontal asymptote. Guys, am I just going completely over your head? Okay. So, let me get through this and we'll do a lot of examples, all right? Okay, so for this one, you're trying to find where it breaks. So the graph that stops between here. And for that, you need the highest y value here and the lowest one here. So if we click on the 2 points where the highest and the lowest values are, we're looking at these two y values. All right. So that means that our first leg of the race goes from negative infinity to negative 10.4 or 10.5. So this graph goes from negative infinity to negative 10.5 approximately. And then we put a bracket there because it actually stops there, it hits it. But if we look again, the graph doesn't pick up again until we get to a y value of negative 1.5. So this would be negative 1.5 to infinity. X and Y intercepts I'm just going to give you because for these two examples, because you literally just look at the graph and click on them. So for time's sake, X intercepts are 0, 0 for the first one and 3/2, 0. Y intercept is 0, 0. For this one, it's negative 2, 0, 2, 0. The y-intercept is 0, negative 4/3. Okay, the last part is end behavior. So end behavior is basically what the ends look like. And the way we write the end behavior is we always start with x approaches negative infinity, y approaches negative infinity. This is when it's coming from the right. This is when it's coming from the left. Now, for these, all right, basically, if you have a horizontal asymptote, that's where your y is going to approach every time. All right, you don't have to figure out if the ends are going up or if the ends are going down. It's really just whatever the horizontal asymptote is, that's where the y approaches. So for this one, our end behavior would be as x approaches negative infinity, y approaches where? What's my horizontal asymptote? 1/2. Then as x approaches positive infinity, y approaches where? Still 1/2. Sometimes if we don't have a horizontal asymptote, we still have to check the graph. So going back to this graph. So as x approaches negative infinity, so all of my x values to the left, all right, which way are both the ends pointing, up or down? Down, so they're going to where? Negative infinity. So as x approaches negative infinity, y approaches negative infinity for this one. As x approaches positive infinity, so looking at the graph. So the right side of the graph, so over here. Where's it pointing? It's pointing up, so it's going to where? Positive infinity. All right, so I know that was a lot of information in a short amount of time. So what we're going to do is I'm going to show you the questions that you're going to have for this on your test, not the actual test questions, but we'll look at your review for that section and go through a couple of them together. Okay, so just finish the notes out, and now we're going to do our reviews together. So once you finish writing, take out your review packet that you got yesterday. We're going to do some questions together. So keep Desmos open. Also, just go ahead and take your 5-minute break so you guys can take a brain break. So have your review packet ready to go, and you guys can go ahead and take your 5-minute break.
Do you want the ice? What is your point here? You get something. We're going. Here it goes. You have it. Oh, no. Then that's okay. Let me see this. Let me see. Let me see. Do you like it anyway?
You guys have your review packet out.
I will never next lay down.
All right. I'm about to show you every method in the book to cheat your way through this test. Well, quote unquote cheat. In other words, use Desmos to your advantage. Exactly. The legal cheating. The cheating that I won't write you up for. Let's put it that way. Catch them every time. Just saying, guys. All right, my dears. So you have your review packet out, and we are going and have Desmos open. We are going to be learning all the tricks. All right, I'm about to show you every trick in the book you could possibly think of. And I'm going to sit down for this because I don't feel like standing up. So I'm about to show you every trick in the book just for the stuff that I just threw at you, as well as the stuff for like all the simplifying and everything else. Now, does that mean this test you still will not be required to know how to solve it? Yes, because there's a couple of short answer on there, but it's mostly multiple choice. I'm going to show you how to use what you know to your advantage with your multiple choice. So the biggest thing is you just got to understand the vocabulary. All right. You got to understand what you're trying to find. And then from there, Desmos can help you. So I'm going to look at the very first question. This is a question that goes with something that we already discussed. So, for this question, it says to find the horizontal asymptote of this function. Now, that's something that we just learned. So, there's two ways to go about this. You could use the cases that we just learned, like based off their degrees, or what did I say an asymptote is? A line that the graph cannot cross. So, what you're going to do is they gave you 4 different lines. Does it have to be horizontal? It's a horizontal asymptote, so does the line have to be horizontal?
Yes.
Yes, so that automatically eliminates which choices? A and C, because if you graph those in Desmos, which you can just to check, they give you vertical lines. So both of these are vertical. And again, you could graph in Desmos just to check it. Now, I'm going to graph the 2 remaining lines in Desmos as well as this in Desmos. And what you're going to look at is see which line the graph does not cross. So in Desmos, I'm going to type in this function. So I have 1 over x squared minus 4. Yeah, that would help if I put the correct function in. So, and I'm going to graph the 2 lines, y equals 4 and y equals 0. I'm going to zoom in a little bit. Which of these 2 horizontal lines, the green or the purple? So look up here. Does your graph not cross? So which of these 2 lines does your graph not cross, the green or the purple? The purple. And that purple corresponds to which function? Y equals 0. Guess what? That's your answer. So if you know that an asymptote means a line graph cannot cross, you can graph all of these lines. You know it has to be horizontal, so that eliminates 2 of your choices. Then you just look for the line that it does not cross. You graph all the lines, see which one it doesn't cross. And make sure it's a horizontal line, not a vertical. Pretty easy, right?
Yeah.
All right. Now, it's asking for which values are not in the range. All right. So range means what? Y values. So what Y values are not in the range? So in other words, it's wherever we have a what? The horizontal asymptote, which they already nicely graphed for you. Where's that horizontal asymptote at? 1. Now they try to throw you off and give you a point that suspiciously looks like a hole, but since this is not an open circle, it's not a hole. So we go based off of the horizontal asymptote, which is at y equal 1. So what's the only y value that cannot be in the range? Boom. X-intercept, obviously graph it, find where it crosses the x-axis. I'm not going to go through that one. Which of the following represents the graph? If you don't graph this function in Desmos, I will judge you completely. So, graph it in Desmos, see which one looks the most like it, all right? Some of them may look similar, so at that point, find points that line up. Happy points on the graphs and in Desmos. See which one lines up. So take a minute, graph it. Tell me what you get. you guys get the answer? It's C. If you graphed it, you will find it looks similar to A or C. From there, you just got to look at some points, see if it lines up. So you can check if it lines up at the point, for example, 6, 16. That's a good happy point that we can obviously tell. All right. 5, same process, but we're not going to do that one. 6, it's asking for the horizontal and vertical asymptotes of this function. We're going to do the exact same process that we did earlier with horizontal asymptotes. But what we're going to do is we're going to graph each answer choice individually so we don't confuse ourselves. All right? So we're looking for lines. The graph doesn't cross. All right? So I'm going to graph this function. So I have x squared plus 2x plus 1 divided by x squared plus 3x minus 4. So I get a graph that looks like this. I'm now going to graph the lines for answer choice A. I'm just going to type in exactly what they have there. If either of those lines cross, it's not an answer. So if either of those lines cross the graph, it's not an answer. So we got x equals 1, and then y equals -1. Is that the answer? Nope. Why? Right, that blue line crosses the x-axis. So not only does that eliminate answer choice A, it also eliminates what? Is there another one that has? It also eliminates answer choice B, because this is the line that crossed. Answer choice B shares the same line in its answer, so that automatically eliminates 2 answer choices. All right. X is equal to plus or minus 1. So plus or minus 1, that means you have a positive 1 and a negative 1. So I'm going to graph these lines. So I can keep the x equals 1. I now have x equals -1 as well, which, what's the problem already with that one? It crosses. So we don't even have to finish it because it's automatically out. So it has to be D, but we're still going to check ourselves. So I have x is equal to 1. I have x is equal to -4. And y is equal to 1. And if we look, it looks like none of these lines will cross our graph. It kind of boxes them in. That's what the asymptotes do. They kind of box the graph in. And so that's how we get D. Pretty simple, right? Like I said, you can do the same thing on the EOC and you can work your way to the answers without actually having to know the math. Multiple choice questions, which is predominantly what your tests and your graphs are for. That's what you do. All right. So the rest of the questions for 4.1 are very, very similar to what we already went over. So let's look at section 4.2. So this was all the simplifying ones that gave you guys a lot of crap. This is probably the easiest sections that you will ever do, because almost all of these are what we call equivalent problems. And what you do for almost all of these, if it's asking for what does this equal to, all you want to do is graph the problem in Desmos, graph all the answer choices, and see which answer lines up perfectly to the original graph. And that's your answer. Now, you do have some short answer on these, and you do not need to skip them because let's see, there's 25 questions on that test, so 4 points apiece. So if you don't answer a short answer question, that's an automatic loss of 4 points. All right, out of 100. So my suggestion to you is you still need to know the process, but if you're really comfortable with the process, by all means, keep doing the mathematical way because in some ways it's faster. But if you struggle with the processes, just graph the stuff in Desmos and save the processes for when you have to do the short answer. All right. Please, for the love of God, do not leave short answers blank. At least attempt them because I will give you some partial credit back. All right. So let's do one that looks a little tougher. So let's do this division one. So I'm going to graph this entire problem into Desmos. So this one has a lot of parentheses with it, so be careful. So I'm going to completely clear out what I got in Desmos. And I'm going to type in big parentheses, x squared. Actually, it's a bigger parenthesis. X squared plus 8x plus 16. Close that parentheses, all divided by x plus 3. Close that parentheses, all divided by parentheses 2x minus 1. No. Why'd you go out of the parentheses? Minus 1. Stop. Minus 1. Another parenthesis out here. All divided by x squared minus 9. So this is what your graph looks like. This is your original. So what's going to happen is that if you graph all of those answer choices in Desmos, your graph will look exactly like that graph. It'll overlap it completely. All right. So if I just plug in those answer choices real quick, and I'm going to type them in exactly as I see them. So I have 2 x plus 4 all squared, big parentheses, no, big parentheses divided by x minus 3 times x plus 3 all squared. Does that look like my graph? Nope. So that one's out. Uh-huh. Oh, it would help you if I read it correctly. Okay, still wouldn't look like the other one anyway. So the next one is 2 times x plus 3 times x minus 3, big parenthesis, all over x plus 4. Does that look like the graph? Nope. Make sure you zoom out a little, but nope, still not. So B's out. Then we got, with our luck, the answer will be D. Y'all watch. So it'll be x plus 4 times x minus 3 all over 2. Does it look like I have 2 graphs on there or 1? 1. They're the exact same. So guess what your answer is? C. That's what it means for a graph expression to be equivalent. All right. So your answer for 12 is C. So again, it depends on what you're most comfortable with. If you're very comfortable with the algebraic way, do it. But if you're one of those that struggle with factoring to get to where you need to simplify it, if it's multiple choice, do the equivalency method. It's a little bit more time consuming in some ways because you have to type it in painstakingly, but it's worth it in the long run. Any questions on those? So you do basically all the same thing from 10 through 14. Just put it in Desmos, find the equivalent graphs. Now, what values of x is the expression undefined are? So, values of x. So with these values of x, all right, you'll do the same thing that we did for vertical asymptotes and horizontal asymptotes. So you do the same thing that we did to find the vertical asymptote. You would set all of these equal to x. Graph them as well as the original graph. See which ones do not cross the graph at all. If they don't cross the graph at all, they're the correct answer, which I can tell you right now it's D. So just to show you guys what that would look like, you don't have to do this, but just to show you. If I graph the original, I have x minus 1 divided by 2x times x plus 1. And I'm then going to graph x equals 0 and x equals -1. So the ones that I said are the answers. If I zoom in a little bit, do those two lines look like they cross anywhere on the graph? Nope. So those are where it's undefined. Undefined means that they're not used in the graph. It's usually either part of the vertical asymptote, the horizontal asymptote, or the whole. Does that make sense for that one? All right. With the adding and subtracting ones, you'll do the exact same thing that you did for 4.2. Their equivalency, you would just put them in Desmos, put all the answer choices in Desmos, find which graph lines up perfectly. That's all you do for those. Now, you got to know how to do 4.4. That's just one that you got to know how to do. All right. So you got to know how to set up the equation. We talked about it yesterday extensively, but honestly, those are probably the easier ones. Like those are pretty easy to do. So those are the only ones I expect you to know how to do for the most part. As well as rational equations. You just got to know how to do them. All right. But if you want, here's another way you could figure out the rational equations. So look at 26. So if rational equations throw you off, like the actual act of solving them, all right, here's a way that you can solve rational equations using Desmos. Same thing, you can use this method for 4.4 as well, but you have to be able to develop the equation first, all right? So you'd have to figure out what the equation is for 4.4, then you can use Desmos. It'll be the same method. So if I'm looking at 26. If I look at 26, what I'm going to do is I'm going to divide both sides of the equal sign. And I'm going to set both of these as y equals this. I'm going to graph them both separately in Desmos. Your answer will be the point of intersection of those two graphs. What value of the point do you think they'll use? What do we typically solve for when we solve an equation? It's the x value of the point of intersection. That's your answer. You can use that for almost any equation. If you have an equal sign, take one side of the equal sign, graph it in Desmos. Take the other side of the equal sign, graph it in Desmos. Find the point of intersection. It's the x value. So just to show you, all right, we have 3 divided by x squared plus x minus 2 plus 3 divided by x minus 1. And I forgot to put the y equals up front. Wrong thing. Wrap app. Guys, I'm about to cuss.
I just see her like trying so hard up there.
Screw it.
Oh my god, I'm dying. You know that one. It's where the speak out thing comes from.
Ugh. When in doubt, just do it again. 3 divided by y equals 3 divided by x squared
What's your view now?
plus x minus 2 plus 3 divided by x minus 1. Then right here, y equals 1 divided by x plus 2. And then I'm finding the point or points of intersection. Here's one of them at x is negative 5. I think there's another one up here. Nope, doesn't look like it crosses again. So there's only one point of intersection, and that is right here. And Desmos lovingly already graphs that point of intersection for you, so you can just click on it with ease. And you've used the x value, so guess what your answer is? B. And you can use that for almost all of these. So like if they put y here, just replace that y with x because you typically solve for x. Whatever variable you're trying to find, just replace it with x. So, feel a bit more confident with this test now? So, the ones that you really need to pay attention to is the ones that like you have to simplify. So, like proportionals, just remember that's just cross multiplication. All right, that's just asking for that expression, so that's pretty easy. Solving, again, you're finding the point of intersection, it's the y value. Just set both sides of the equal sign as two different graphs in Desmos. The word problems, the hardest part is the setup, and you have your notes for that. All right. So use your notes to set it up, then you can use Desmos to solve it. All right. Any questions on any of this? I've already posted the key, but now you got all your little tricks. All right. So my suggestion to you is continue to work through this review using those tricks and check yourself with my key that I already posted and see how you do. All right. Because it's not necessarily a hard test if you can use your calculator to your advantage. All right. There's a couple of short answer, but I think there's only like 3, maybe 4 of them. So still need to know how to do it algebraically for a couple of problems. And my suggestion to you is please, 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 please try those short answers because I can give you partial credit back. All right. Those are the only ones that I give you partial credit back. These, right or wrong. All right. Multiple choice, right or wrong. So that's when you want to use Desmos to your advantage when you have multiple choice questions. All right. Does that make sense? All right. And again, EOC, all those tricks I taught you, they translate not just in this unit, but in others too. All right. Okay. So you guys got about 15 minutes until class ends. So I'll post the exit ticket. And then you guys can also work on any other work you have for right now. Also, there is a new Delta Math for 4.1, but I think it's only like 5 problems. It's really quick. So you can knock that out pretty easily.
Sounds fun. You were studying
The Desmos one?
the Desmos stuff I understood. The other
Yeah.
stuff.
And that's why I showed you all the